For decades, the exact science of how the northern lights form in our night sky has eluded experts, and we have finally proved just how these dazzling light shows happen. Auroras appear in the upper atmosphere near the poles, and they were first mentioned in texts thousands of years ago. But it wasn't until the late 1800s that a Norwegian physicist first made the connection between electric currents in Earth's magnetic field and auroras in the sky. And it's only been since the beginning of the 20th century that scientists have known the basics of how auroras work. Today we know that all auroras begin with solar activity. The sun puts out a continuous stream of charged particles called the solar wind. These energetic particles strike oxygen and nitrogen molecules in the atmosphere, bumping them up to an excited state. When they relax, the molecules emit photons that light up the night skies, producing beautiful auroras. Occasionally, the sun will burp out a coronal mass ejection or solar flare, sending electrons slamming into Earth's magnetic field in what's called a geomagnetic storm. They're responsible for producing the most intense auroras. They disrupt the magnetic field lines, creating ripples that rebound back toward Earth, known as Alfvén waves. And this is where the mystery starts. For the last 40 years, scientists have hypothesized that electrons can accelerate from space to Earth, and they do it by surfing on Alfvén waves. Any surfer will tell you that the key to catching a wave is paddling along with it. If you paddle close to the speed of the wave, you'll be picked up and accelerated. The energy transfer from the wave to the electron happens through a phenomenon known as Landau damping. But up until this point, scientists have struggled to prove this theory, so they did what scientists do and decided to recreate it in a lab. To see if electrons were accelerated by the electric field of an Alfvén wave, the team had to scale the vast distances of space into the confines of a lab. For this, they turned to UCLA's Large Plasma device. This nearly 20-meter-long cylindrical chamber creates a field of highly charged particles called plasma. The team also had to develop new instruments and techniques to detect a very small population of electrons moving within a narrow range of velocities. The experiment went down like this. The plasma in the chamber forced electrons up and down the magnetic field. A specially designed antenna sent Alfvén waves down the chamber. Further down the chamber, the scientists used the two new sensors they created to measure variations in the electric and magnetic field and the electrons in the plasma. And they were right. The data showed a small population of electrons, like we're talking less than 1 in 1,000, surfing on epic Alfvén waves. So now that this hypothesis has been proven correct, what's next? The techniques developed in this study can help scientists better understand other phenomena in space where particles are energized, like how the sun's corona is heated to 1,000,000 degrees, how cosmic rays get close to the speed of light, or how radiation belts like the one near Earth affect satellites that we depend on for communication and navigation. So next time you take a look at the dancing lights in the sky, remember the 4-decade-long mystery and how solving it will help us better understand the vast universe that surrounds us. If you find the magnetic field that helps produce Earth's auroras interesting, you should check out Amanda's video on Mars's magnetic field. If there's a space breakthrough you'd like to see us cover, let us know in the comments below. And as always, thanks for watching Seeker.